test in the chat. See if that is working. Right. Yeah, I think we're going to start off today actually with a bit of Git cleanup work. For the last probably over a month, I was working on debugging some pretty difficult bugs with multi-core bring up and stuff like this, but that's finished now. And so now I can clean up the branch and kind of squash some commits and stuff. And then we'll move on to working on the round robin scheduler as part of lab 4. Yeah, so let's just kick things off. I'm going to be working on, this is the branch I need to clean up. And there's a bunch of stuff that can get squashed here because I merged the lab 3 code into lab 4, into the lab 4 branch, and then needed to fix a bunch of stuff that got broken. And then I was working on some of the exercises, but yeah, there's a bunch of random stuff. Hello to everyone joining the stream. Welcome. Okay, hopefully all the Twitter and Discord things worked. So let's take a look. Oh, first off, let's just run the kernel and make sure that it's working and it's in the same state as last time. So when we stopped last time, what we were able to see is that we were able to boot up a multi-core system with a bunch of different CPUs, which we're seeing here, and then we're able to execute a very, very simple user space program on CPU 0, which executes a divide by 0, which triggers an interrupt, which the kernel on CPU 0 handles, and then it destroys the process and then basically halts, because there's no other processes that are runnable. And so that's good. That's like a totally working state, and we can continue working from there. So that means we're ready to do a bit of cleanup work. So basically I'm checked out to the October 6th debug branch. I'll do the cleanup work, and then when I'm done, I'll make lab 4 point to whatever state we end up at. So yeah. There's it's actually a bit overwhelming of where to start. Because there's just a bunch of stuff here, but let's just begin by reading through it and understanding what is in this branch. So the first thing I do is I fix some error that I think broke the build in the merge. So I fix this bug. I fix another bug. Apparently I left this in kind of a not great state. Yo, what's up, Ali? Good morning. Actually, we're in a bit of a time zone out of sync situation between the US and Germany right now. So I think I'm starting 1 hour later than usual than I do in the US, but it's still 4 p.m. here in Germany. But yeah, morning, Ali. Hope you're doing well. Yeah, so I'm cleaning up this Git branch. So we have these 2 fixes. So this is my fix for the boot bug that got created when I merged in my code into lab 4. Then I started working on some of these exercises, exercise 1, exercise 2, remove panic. That's in pmap.c. Yeah, so this can very obviously be squashed. In this commit, I had this panic 333, then I remove it in the next commit. So I'm just going to fix that up. So now it no longer panic 333s. So that's a start. What's up, Afnan? Thank you for the test too. Yeah, hope you're doing well. Thank you, sir. Yeah, I got the haircut yesterday. All right. Disable test. I think, yeah, this is actually important. Yeah, there was like some unit tests for the page directory and then for the kernel page directory, and I ended up reusing them on the environment page directory just to make sure it was in a consistent state also, but we're kind of getting to a point where they start to diverge, I suppose. So commenting out that test for now. Exercise 3, map per CPU kernel stacks. Yeah, this has this boot stack comment. Okay. Disable. Okay, so now we are completely into debugging world. And this is not really a commit that belongs in the production code. This is a commit that I introduced just for debugging. This is another one. Right, this is another commit that's pretty much just for debugging. We could probably safely get rid of it. So I'm just going to test that out by reverting the commit. And then let's see if the kernel still runs. Yes, that ran perfectly. Okay, so that's a good sign. That means that print commit can go. We do not need any of this anymore. So what I'm going to do is I'm going to drop this commit and I'm going to drop this commit. Okay. Moving on. Fix. Make n set of VM consistent. What did I fix here? Okay, so right. So here's me fixing a bug in kind of like copy pasted code, if I am reading this correctly. Yeah, I think actually we're going to drop this commit too. So what happened here? Originally, I had a bunch of copy pasted code in two places. I had a bunch of code for setting up the virtual memory of the kernel in one place. And then in a separate place, I copy and pasted a bunch of that code to set up the kernel portion of a process's virtual memory space. And I did a bunch of work and updated some of the code in the first area for the kernel setup, but I forgot to replicate that for the second area. And that caused an issue. And so now I have this commit which tries to fix that by making them in sync. But later, I make this whole thing obsolete by removing that copy and pasting entirely. And that happens here in this fix commit. Simply, yeah, I delete like all of this code, including or maybe not. Wait a sec. Well, wait a sec. So, and instead of, we're talking the thing right before envs, right? Okay, I see. So this code mutated in the meantime. But I think, yeah, I think the fact remains that we can delete a lot of stuff. So I think we can delete this commit. What is this commit? Support multi-core by mapping all kernel stacks into the env. Again, I think this is going to be totally obsolete. All of this code is mutating this env setup VM, where in a few commits, we're going to drop just like all of the code. So what I think we can actually do is just start deleting stuff left and right. But if I just delete a commit out of the middle of this history, like if I, for example, delete this commit right now, it's going to merge conflict later, I think. Let me just try it. Yeah, abort the rebase. It's going to merge conflict later because future code depends on this thing. So what I actually want to do is I want to, man, how do I want to start an interactive rebase, right? And I want to drop this, keep this, keep that, keep that. So I want to drop these two commits during one interactive rebase. And I'm hopeful that this is not going to conflict. I guess it does. Let's see why. What is it in env dot, oops. Okay. So we have this conflict, but ultimately the final state of this code just needs to be this. So I copy and paste this code. I believe this is all pretty much the same. I see. The difference is in this hunk, this for loop. Yeah, the for loop was in the original history, but I dropped both of those. Anyway, the resolution of this thing is just to keep the final one. So I'm going to accept the incoming change. Yes. Let me get my, okay. So that's, let me make sure things, okay. So I think I resolved this. Let's just run it again just to make sure. And yeah, we're still running. 8 CPUs start up and we trap on the first one. No runnable environments. Everything's working perfectly. Good. We're making some progress. This branch is starting to look nice. What I'm going to do is I'm going to reorder some of these commits actually. I'm going to bring this one all the way down. Like the general category of these commits is just kind of like fixing up random stuff that's kind of broken, that wasn't really related to what I'm doing. This is eventually, actually I think this one is going to go all the way to the start of the branch also. So this is like, these two commits are just kind of like fixing the bit rot of the project. Yeah, this one is also fixing the bit rot of the project. And then this one is actually fixing broken code that I wrote, but I want to just do that before we start doing anything else. So, because that's been a very long-standing bug. And then finally, we will have the commits for implementing the exercises. Let's see how this goes. Yeah, there should not be any merge conflicts, and there were not. one more time to make sure it runs. Good. Okay. Okay, I have some good. I'm just going to okay, now what are we doing with these? So this thing, okay, so this, all right, so this, I think I'm going to move this one down also. Just for fun, I'm going to re-enable this. I believe it should fail. Oh, interesting. Okay, no, I guess we can leave. We can just leave this. You know, we can even, I think we can even just delete this line. Now that, like, the whole purpose of having this check line here was to check all of that logic that we have now deleted. I think it's kind of irrelevant, actually, or redundant, because now we're simply just copying this existing page directory which has been set up, and that's already been vetted and confirmed. So I'm actually just going to delete that. Room comment. I'll figure out what to do with that in a little bit. Actually, so yeah, I'm just going to drop this, drop that. No conflicts, good. Fix, and then now we start these exercises. The kernel should still run, hopefully. Yes. Okay. So now this is getting really into debugging world. I'm going to just move this up. I think I'll just fix this up. It should still work. Yeah, nice. Okay, so now we're converging on kind of the final production state of this branch. Fix a bunch of these merge weird bit rot things. Fix a core bug of mine. Then implement the exercises. And I think actually, I mean, yeah, this is not really a production commit anyway. This is just for my testing to execute this div 0 thing. But yeah, but like I said, that's just for debugging. In the production code, we're actually going to want to retain this scheduled call. Yeah, so I think actually that does it for the cleanup that I'm after. I'm pretty happy with that. And what I'm going to do is I'm just going to record some timestamps. So we're at 19:28, finished, git cleanup. And then next we're going to do round robin schedule. I kind of want to try adding chapters to my YouTube videos, so it's helpful to just record some timestamps. Oh, I just realized, is the music not playing? Or is OBS just not? I guess not. Oh, I thought there was the hip hop music playing this whole time. That's too bad. Okay, hopefully it should be going in the background now. Yeah. I just realized. Let's take a 20-second break to stand up and stretch. I think we're due for one of those. Be right back. Okay. So we're back, and now we're ready. Yeah, just to check in. Okay, let's check in on the rest of this stuff. I did exercise 3, I did exercise 4. Locking. Apply the big kernel lock by calling lock kernel. You know, I kind of remember, like I thought I did this, but now I'm not seeing it. I'm going to just search my ref log quickly. I don't know really what happened to this commit. I remember doing it, but I don't see it at all anymore. Let's take a look. I'm just going to cherry pick it. My local changes. Okay, I'm just going to stash my changes, cherry pick this thing. Let's see how it looks. Anyway, yeah, this is what my attempt at doing exercise 5 was. It's been a while, so let's maybe confirm that it's correct. Okay, let's review. Yeah, so locking. So basically, yeah, we did all this work to set up the bring up of all the other CPUs on the system. And that's cool. That means now we can make use of the other CPUs and run code on them, which is potentially good for performance. But now that means we need to deal with all of the concurrency and parallelism issues that comes with having multiple concurrent streams of execution. And so locking is a natural first solution there. And it says, our current code spins. Before letting the API get any further, we need to address the race conditions when CPUs execute kernel code simultaneously. The simplest way is a big kernel lock. A single global lock held whenever we enter kernel mode and released when the environment returns to user mode. In this model, environments in user mode can run concurrently, but no more than one environment can run in kernel mode. Any other environments that try to enter kernel mode wait. So we have this one big spin lock with these kind of like global functions. And it says you should apply the big lock at 4 locations. Okay, let's just make sure I did this. So first up is i3d6 init lock kernel. Yo, what's up, Groove Chemist? Thank you very much. Yeah, I think it's a cool t-shirt also. So acquire the lock before the BSP wakes up other CPUs. We're doing that because we want to make sure those other CPUs don't like accidentally start executing too far and create race conditions. And so we're just going to grab the lock, and we do that right here. Grab the lock, and then we boot the application processors. Next, in MP main multiprocessor main, acquire the lock after initializing the AP, then call scheduled to start running environments on this AP. Let's check that out. Acquire the lock after initializing the AP. So here we're doing the setup code that runs on the application processor. We just do all the basic bring up stuff. Then we lock it after initializing and then call schedule. So that looks kind of correct to me. Next in trap, acquire the lock when trapped from user mode. So let's check out trap. So here we are like processing an interrupt or exception on a particular CPU. And before we get really into the kernel, we need to check if we trap from user mode and then acquire the lock. We were doing that, yep. Looks correct to me. In env run, release the lock right before switching to user mode. So this is kind of the opposite of this right here. Here we are entering the kernel on an interrupt or exception. Here we are leaving the kernel and dropping into user space. And apparently I chose to do this right before this env pop tf function. I wonder, I mean, I suppose it's possible also to do it even later. Do not do that too early or too late, otherwise you will experience races or deadlocks. It says right before switching to user mode. It's possible that this is actually a little bit too late. But I'm not sure it really matters. I mean, the most strictly conservative placement of this is going to be literally like kind of right here, I guess, in env pop tf. You know, maybe it's best to just do that. That's basically the smallest window. I guess what could happen here is we're in one process, the process traps into the kernel, it's doing some stuff. In the meantime, another CPU is running a program and it tries to trap into the kernel, but this thing is locked still over here. We have not unlocked it yet. So that secondary CPU is going to have to wait. It's going to spin on the spin lock. Here, we're going to unlock the kernel, and as soon as we do that, the other CPU is eligible to begin executing code in the kernel, and it just goes ahead, which means for this brief period of time after this thing returns, and for the duration of like env pop tf, which is this stuff, 2 CPUs will be in the kernel simultaneously. And that's not necessarily an issue unless they are accessing and mutating shared data. And I'm not particularly, I don't really think that's what's happening here. I think so. Let's say in the worst case, we unlock the kernel here and another thing immediately starts to execute at the same time. What do we do? All we do is we call this function. We're accessing this trap frame thing, but these trap frames are going to be on separate kernel stacks. So there's not like any shared data happening there. So that is fine. We're going to access the CPU num, which involves involves accessing the lay pick, which is also private to each CPU. So that's not going to be a data race either. We save that into this env CPU num thing, which is also per CPU, so that's not shared data either. And then lastly, we just like set our stack pointer all the way back to the trap frame. We pop a couple things off of the trap frame that's like our custom stuff that we added that the CPU doesn't understand, and then we just iret, and then the CPU like kind of takes this trap frame off the stack, interprets it, and then drops into user space. So that's just kind of all to say that I don't actually believe there's any kind of race condition that would happen as a result of putting the unlock kernel call here. So in the interest of keeping it spicy, I'm just going to leave it there and hope my understanding is correct. Okay. Yo, what's up, Guru Prasath? Welcome. Okay. So okay. So I've been wrong before, so let me put my money where my mouth is and run the kernel and see if it still works. I really hope this works. Ooh. Okay, well, this is interesting. This is very interesting, yeah, and I don't know. So I'm just gonna start making sticky notes as usual. So, added back the exercise 5 lock kernel commit. Things were totally working before. Now we hit this assertion. Which is kind of mysterious to me. So, okay, well, I guess we're back in debugging world. Okay, maybe, okay, just to quickly test this, maybe I was totally wrong. Maybe actually there's some reason where the unlock kernel thing needs to be later. Nope. Okay, same thing happens. So I'm going to undo. Good. Assertion failed. So the interrupt flag. It's asserting that we should not have the interrupt flag raised, I suppose. And I kind of don't understand that, actually. I'll need to refresh myself on these details. Oops, okay. But I could have sworn. Okay, let's just try to understand this then. So here we are in trap. And here, check that interrupts are disabled. If this assertion fails, do not be tempted to fix it by inserting a CLI in the interrupt path. Or a trap entry. So What I don't really understand is how does this code I wonder if it has to do with this calling scheduled. So I think I actually already implemented. Okay, no. Oh man, that is kind of a bummer. Again, must have, I know. Man, I definitely, yeah, okay. For some reason, I lost a bunch of commits somehow. Okay, yeah, I'm just going to, I don't know, save this commit hash somewhere. So yeah. Okay, so I don't have the scheduler yet. Well, let me read this a bit more carefully. Yeah, I'm not really getting how any of this is related to that. The one thing I think I could try here is just making sure the APs really don't do anything. So you know what, I'm even going to just do this. Does anything change? No, nothing changes. Oops. Let me just go down to one CPU. Yeah, that's interesting. So that doesn't change anything. I'm going to I'm going to revert this. Okay, I'm going to delete this. I'm going to revert this. And it's working. Oh, actually, wait a sec. No, what? Oh, wow. It's not working. What? Wait, what? Was it working with 8 CPUs? Wait, what? How is this possible? I'm so confused. Wasn't this all just working? All right, let me. Okay, well, at least though, I mean, this is kind of unfortunate. At least I saved where I was. this should still be working, right? Right, so this is still working. So the lab 4 thing is still working, but somehow... Okay, that's... Okay, what? I don't understand what just happened. Like... Alright, 20-second break. Just stand up and stretch. Be right back. This is crazy. Okay, well, I'm definitely not debugging that all again. It must be something very... Or maybe it was on all this reordering. Is it somehow possible that I forgot something? Okay, maybe I'll just try again. 27. Debug. Let's just try this again. Okay. So being very careful now, we're going to fix this up, right? And it should still work. Still works, okay. We're gonna move this all the way down here, basically. That should definitely still work. Okay, we are going to drop this commit. Should still work. We're going to drop both of these. What happened? Okay. Yeah, we're going to drop both of these, which resolves in a tiny conflict, which we already resolved. All we want is this incoming change. And that still works. Good. Okay. We're gonna move this one down. We're gonna move this one down. This should still work. Still works. I'm going to fix this up. Should still work. Still works. I'm gonna make a delete. I'm gonna delete this commit. It should still work. Still works. I feel like I'm converging on exactly the same state of the branch. Oh, wait, was it maybe? This was the part that I changed, right. Let me go back here and apply the stash. So this should work. Right. Interesting. That was the part, yeah. So now I've reverted this. Let me delete this revert. What happens now? Now we start to run into this assertion failure. Okay, so the big lock and commit creates the assertion failure. And as a separate kind of thing, without the div0 commit, there's this kernel page fault. Which is like code name for some kind of kernel crash. It would be really nice to get more information about that kind of stuff, such as the cause of the crash or the register state or something. But so I guess for the moment it's executing. So it was. So the kernel was maybe crashing on this user primes program. Yeah. So okay, so maybe I don't mess with that for right now. I'm going to I'm just going to commit these two whips, which will allow me to investigate this, yeah, this thing, this interrupt flag issue. Kernel panic on CPU 5. Does it change CPU numbers every time? CPU 2. That is interesting because none of these CPUs should be doing anything. Okay. Apparently they are. Wait, what? Okay. So apparently these other CPUs are trapped. So now we're hanging. What is here? Sched halt, right? Okay. do one CPU. What about that? So that works. What happens if we... Oh. I'm just going to commit this all, so while 1 to stop APs. Oh no. Get revert abort? Is that a thing? Okay. Actually, yeah, I'm just going to bring this all the way, or rebase. Edit this, I'm going to revert this commit inline. Okay. So before I added any of this, okay, revert this, then I'll revert this. So before I added any of that locking stuff, things were all good. So the working state is np main. The working state is these things just spin. They just completely spin. They notify the main processor that they've woken up, and then they just spin. Okay. Now we introduce this code, which changes things. Instead of just spinning, the key difference is that they start to lock the kernel. Let me suppress even that part. I think we should hopefully see the same thing now. Yeah. So 8 CPUs come up. CPU 0 traps and exits. So that is good. All our problems begin once we try to acquire the lock. That's when all our problems begin. Or is it? Like, what is even happening here? Oh, I see. Okay, I have the weird suspicion that this CPU is weirdly like, getting the lock. Okay, see. I don't think it should not be getting the lock. Why is the CPU getting the lock? It should not be this indicates that do we somehow unlock? We lock the kernel and then boot the APs. It seems like this is not working. It seems like this call is not actually working for some reason. Okay, I'm just going to try to debug this, I suppose. Did this not work? Okay, it's crazy. Hello? I forgot to continue, okay. Init, MP init, white pick init. Lock kernel. Step. Okay. We pick. What's the actual variable? P kernel lock. So it's locked 1, right? So so now we're booting the CPUs. Hey, what's up, RevOrg? Did you go to university to learn about this stuff? A little bit, but honestly, no. What I'm learning about this stuff by following this university class, actually, this MIT class. So this is my form of going to university to learn this stuff. The vast majority of majority of what I'm doing, I learned by streaming, actually, just on these streams. If I break MP main, so now I'm thread 2, it says. Is the kernel lock is still locked? Oh, does one of these? Is it possible that one of these unlocks the lock? No way. Infinite? No way. That should not be possible, but I'm just checking anyway. Nope. Okay. Okay, let's check our lock. Still locked. Let's step into lock kernel, step into spin lock. Why did that return? This is really small. Huh. Seems like the APs are executing even when VSP holds a kernel lock. CPU 1 starting. Okay, I see. Okay, so this looks like it's working. So now it's actually spinning. Never mind. Currently learning reverse engineering across a few different online resources. Let's pick up on a couple of things you're doing, and it's cool to see. Oh, nice. Very cool. Yeah, no, I spent a good amount of time learning reverse engineering years ago in the CTF scene and stuff. And yeah, I think, yeah, it definitely comes in comes in handy. Just the idea of stepping through code and stuff. Okay, so now good. This is good. We are spinning in the spin log, which means this is working. I was a bit surprised to see, what's this return result? Is it the exchange? That's it, okay. We're spinning in the exchange. So what happens if I continue? But also the 3.3 printed. Well, let me try that one more time. Log kernel. Hit MP main. Okay, I'm going to hit next. Yeah, what the hell? We should not be here. Oh, and now I'm spinning. This while one. Now this thing is saying it's running a load ICO new env. Wow. Man, I'm confused. Okay. It really seems like the spin lock is failing. So after boot APs, somehow the main thread finishes and hits env run. I kind of want to put it, I mean, there's all these how do I enable all this debug spin lock stuff? Oh, is it enabled already? Comment this to it. Is it possible that this spin like debugging is messing me up? That would be kind of funny if it was. All right, 20 seconds to stand up and stretch. Be right back. Okay. Well, this is tricky. So I'm commenting this out and just running this. I don't really expect the difference. It's still hitting the 3.3, which is so weird. Okay. I think I need some more prints. Boot APs. This thing spins. Yeah. This thing spins on the CPU status. Oops. Which this thing sets. Huh. But this thing should be holding the lock the entire time. Oh, but wait a sec. I think I see. I think I see now. That's the problem. So here's what's happening. At my main thread, the main CPU, it grabs the lock. Then it starts triggering the code to wake up the other CPUs. The other CPU wakes up. The main thread hangs, waiting on the other CPU to signal that it has woken up. So it's hanging. This thing starts running and then signals that it's woken up. So then the main CPU continues running. This one continues running too. But the bug I have is because of this thing that I added, where I patched in an end run, which drops into a process and releases the lock. I need to not have that. I need to actually hit run scheduled, which will do a sched halt. So this should behave better. Oh. This should behave better. Did that behave better? Did I forget to save? create. Load iCode. This should all be fine. Let me add another print. Okay. It is so interesting that we're hitting this. Who is unlocking the... Okay, here's what I need to do. I need to be like, I need to say something like unlocking lock from CPU num, just to see who, and maybe I'll just have a, does this work? Okay. Lay pick H. Spin lock dot H. Does this work? No. Okay. Unlocking lock from CPU 0. Locking from CPU 0. So now we're getting interleaving output. Kind of hard to read. So locking from CPU 0. CPU 1 starting. Locking from CPU 1. CPU finished boot args. This thing succeeded. New env. Load iCode. About to run scheduled. Unlocking lock from CPU 0. How? Just go to halt. Oh. That's why we released the lock. Let's say we didn't do that. I don't think we're gonna see this 3-3 thing. Panic cannot acquire, yeah. Oh wait, what? CPU, man, this is crazy. CPU, if holding, what is this? If we are holding, we're already holding it. So, about to run scheduled. I guess I'm just gonna debug this, I suppose. Boot APs. Finish booting. Locking from CPU 1. Right. Got run scheduled. Step. Now we're putting it into a halted state. And then doing what? And then we like, then the CPU stops. Okay. And that's the end because the other CPU can't do anything. Okay, I see. But what, okay, so maybe this is supposed to happen. So maybe this makes sense. We unlock from CPU 0 as part of the halting process. But then why does it say locking from CPU 0? How is it? I don't think that's possible. I feel like that must be some kind of bug? Maybe I'm going to say, maybe I'm going to just add one that says like, got lock from CPU. Got lock. Got lock on, yeah. Got lock on CPU 1. Locking from what? Hello. Does execution continue somehow? No. Well, I'm so perplexed at who is doing this locking from CPU 0. Enable interrupts. Yeah, I'm just going to debug it. Okay. B set halt. About to run scheduled. Right. Now we're in there. We're halting. Load the kernel page dir. Put ourselves into a halted state. We unlock the kernel, which should make the other one immediately wake up. Is it? Oh, wait a sec. Is it possible that the process of halting this CPU like somehow makes CPU 1 become CPU 0 or something? Doesn't really make sense because it says got lock, CPU1, got the lock. Then this thing. Info threads. Info threads. This is kind of cool. So now I'm on the while one. But why did it say locking from CPU 0? Maybe it's a delayed message somehow. Okay, I'm going to I mean, this seems like it's mostly working, I guess. Yeah, sched yield. And this thing just hits sched halt also. Or wait, but no, it doesn't, because there's this infinite loop there. I kind of want yeah, I want some kind of print saying like halting on CPU. Does this work? Wow, now we're hitting this assertion. Is that just because, is that only because of this thing? What? Okay. Maybe a lot, maybe, yeah. This is some like weird interrupt thing happening. I have some suspicion that maybe just continuing with these labs and exercises will make all of these problems go away, maybe. So this might be a long shot. I'm just going to stash everything. Yeah. So here we have this thing. I actually need to, the one thing we need to not stash was this thing. We need to not do this, we need to do this. Want to do right now. All right. So now we're kind of back at our like kind of iffy state where So do we panic on anything? But it seems like we're always panicking. Oh no, this is CPU 6 now. Now we're panicking on this. But it seems to mostly be on CPU 0. Whatever. I'm just going to see if I can continue. I'm just curious what happens if I cherry pick this commit. This was my kind of dumb round robin scheduler. That was exercise 6. Complete round robin scheduling as described above. Don't forget to modify syscall to dispatch yield. Did I do that? I don't think I did. It's saying implement round robin scheduling. It's scheduled, which I have done. I did not do this. Make sure to invoke this in np main. Modify it to create 3 or more environments that all run yield.c. You should see the environment switching back and forth to each other 5 times before terminating, like below. I have some serious doubts about that this will work if I implement it, because I don't think this assertion... Yeah, I'm getting bad vibes about this assertion. And honestly, I don't really understand even what the motivation is. I might actually ask ChatGPT for help. Yo, what's up, Bob? Watching this to get inspired to do my Risk 5 assignment. Dude, I feel like this is a very depressing stream, if anything. But if it helps, it helps. I'm gonna ask ChatGPT now, because I can't figure this out. I'm also gonna not do a geometry break. King on has this. Oh, whoops. This is in the interrupt handling path. Okay. Assert that interrupts are disabled. properly disabling interrupts should have been done before entering this interrupt handler. Okay, I'm gonna ask. I need a bit of more help. Is a distinction between interrupt gates and exception gates or something, and one of the differences is the behavior to the interrupt flag. Am I right? And can you explain this to me? Okay. Interrupt gates and trap gates. These different gates have specific behaviors regarding the interrupt flag, which determines whether the processor can handle further interrupts. Okay, IDT holds descriptors to handlers for various. Each entry can be configured as a different type of gate. It means being interrupt and trap gate for exceptions and some. When an interrupt is invoked through an interrupt gate, the CPU automatically clears the interrupt flag. This means further interrupts are disabled. So that's what we want, right? Prevents nested interrupts. Trap gate. When an exception or interrupt is invoked through a trap gate, the CPU does not clear the interrupt flag. This means that interrupts remain enabled. Allowing interrupts during traps can be useful as traps are often synchronous and predictable events. It's sometimes necessary for the system to continue handling. This looks so daunting. How did you get into kernel? Dude, this is daunting. This is very daunting. I kind of don't know what I'm doing, and I'm trying to figure that out. I got into kernel dev just by deciding that I wanted to, and I started streaming it one day just by following this MIT course that I'm following. That's pretty much all there was to it. I've just been learning on the go this entire time. So here's where we set up the trap gates. And this is trap thing. Setup. I'm just gonna take a screenshot of all of this. And maybe a screenshot. Hello. Maybe I'll just copy all of this. Let's read this. is trap. 1 for a trap, 0 for an interrupt gate. The difference between an interrupt is the effect on IF flag. An interrupt that vectors through an interrupt gate, thereby preventing other interrupts. Subsequent IRET restores IF. An interrupt. So right now I like entirely have is trap which is somehow used to set this gate descriptor type thing, which means that it's not changing IF, but I kind of thought I did this correctly. If we go back to the original thing I was following, but maybe I think, like, so far I think I kind of did this right, actually. Okay, but I think one other thing that might be messing me up, as I think somewhere in the code they also started doing this pick initialization, which is now starting to send hardware interrupts all over the place. And I think, what if I, okay, let me just come back here. I'm just gonna run this. Holy crap, why is it saying received page fault in kernel mode? What? What is going on? Is it because of this round robin scheduler? It might be. Okay, now we're back. Okay, crazy. Okay, so, well, it appears that, it also appears that my round robin commit is crashing. Yeah, this is crazy. It also appears to be crashing. So here I'm back at the status quo. And we're panicking on this thing. I wonder if I just stop doing this. I kind of think we might not see it. No, we still see it. Okay, I'm wondering a couple of things here. One thing, I think one like kind of obvious thing I could do is just change the type of all these gate descriptors to be like interrupt gates. I still don't totally understand. I'm going to ask ChatGPT, when I'm declaring my interrupt trap gates for divide by 0, breakpoint, page or GP fault, page fault. How do I decide whether I should make them interrupt or trap gate? Use an interrupt gate when you want to ensure that no further interrupts can occur while handling the current exception. The handler needs to complete without interference. Use a trap gate if you don't mind other interrupts occur during the exception handling, and allowing them can improve system responsiveness. The exception is predictable and non-reentrant, so it doesn't require protection. Let's apply these guidelines. Divide by 0, trap gate. Divide by 0 is a synchronous exception that occurs due to a specific instruction, meaning it's deterministic and does not affect system-wide state. To maintain responsiveness, that is interesting. Interrupt gate. So, I don't know, based on ChatGPT, I'm not doing the recommended thing actually. Let me see. Seems like I'm doing this wrong for GP fault and page fault. Would that? Okay. Yo, what's up, Carlos? What do I do for a living? I'm a programmer at a music technology company. Yeah, I work at a real company. I do not do operating system development there, though. Well, let's just try with making this 0, 0. Unhandled trap in kernel on CPU 7. This is crazy. I kind of have the feeling I have the feeling that they enabled the timer interrupt, and that's just like messing everything up. This is crazy. Okay, I don't know. I strongly I guess I've even like, why is this necessary? Why do I need to have this code running right now? Well, unhandled trap and kernel. This is I'm deep in the weeds and I have no idea what's going on. And I'm getting a GP fault on CPU 7. Unhandle trapping kernel. And what does that mean again? That means an interrupt or trap happened. We did not handle it. And it did not come from user mode. It came from kernel mode. And apparently it was a GP fault. Oh, all right, well, I think I'm actually out of time today. That was a really deep dive into kernel debugging yet again. But yeah, we'll see. We'll get back to this next time. And we'll see how to proceed with all the various things that are going wrong, which are this interrupt flag assertion, which is failing for some reason. I'm thinking I should not be using so many CPUs, maybe. Maybe I should go back, yeah. Even going back to one CPU. But was this due? What did I change? I just changed these, I just changed these two things. So now if I bring them back to being trap gates, the assertion fails. But is there an easy way for me to quickly see I just print I'm just gonna print every trap frame. GP faulting. Okay, then yeah, we're gonna look into this next week. I'm gonna end the stream here. Thanks a lot for watching. Feel free to join the Discord if you want. Here's the link. Feel free to like, comment, and subscribe if you enjoy what I'm up to. I stream every week at this time. And yeah, I will see you next time. Peace.